Today, we're going to crack the code that chemists use to classify, well, everything in the entire universe. We're talking from a single tiny atom all the way up to a distant galaxy. We're getting right down to the basics of what stuff really is. So let's kick things off with a little bit of a puzzle. What on earth do a gold coin, a simple glass of water, and a bowl of vegetable soup all have in common? I mean, they seem completely different, right? Well, hang in there because by the end of this, you are going to see the hidden connection. So here's our game plan. First, we'll dive into how chemists actually look at stuff. Then we'll put that stuff through what I'm calling the size test. After that, we'll explore a full-blown identity crisis. And then we'll organize it all. And trust me, you are going to want to stick around for that last part where we find out what happens when all these rules we've learned just break. All right, let's dive right in. Whenever a chemist looks at anything, a rock, that glass of water, even the air you're breathing right now, they start by asking two super basic questions to figure out exactly what it is. And it really all boils down to two categories: physical properties versus chemical properties. Think of physical properties like a substance's current stats on a video game character. It's what the substance is right now. Chemical properties, on the other hand, are all about its potential, what it could become if it gets into a reaction. So physical properties are anything you can see or measure without actually changing what the substance is. We're talking about things like its color, its mass, its volume, or the temperature where it melts. You can measure all of these, and at the end of the day, you've still got the exact same stuff you started with. Now, chemical properties, these are all about transformation. Can it catch fire? Is it going to rust? Will it start bubbling and fizzing if you drop some acid on it? To figure these things out, you literally have to try to turn it into something new. It's all about its hidden potential to change. Okay, let's add another layer to this classification puzzle. It's time for the size test. And we're asking a pretty simple question here. If you have more of something, do its fundamental properties actually change? This brings us to what we call extensive properties. These are the traits that get bigger as the sample gets bigger. They scale with size. Mass is the perfect example, right? A huge boulder has way more mass than a little pebble. Same with volume and length. The property literally extends as you add more stuff. But on the flip side, we have intensive properties. And these are the true fingerprints of a substance because they don't change with the amount. Gold is gold-colored whether you have a tiny fleck or a giant bar. Water boils at 100 degrees Celsius whether it's one drop or an entire ocean. These properties are internal to the substance itself. Now, here's a fantastic little trick to remember the difference, and it's one of my favorites. Intensive stays independent of the amount, while extensive expands with the amount. It's a simple little mnemonic, but you know what? It works every single time. And this idea is so important. Just picture it. You've got two chunks of sulfur. One's big, one's small. Their mass, that's an extensive property, is obviously different. But their bright yellow color, an intensive property, is exactly the same for both. That's why these intensive properties are the real key to figuring out what a substance is. Okay, so we know that substances have all these properties, but what happens when those properties actually change? Well, this is where we get to the identity crisis. Is the substance just putting on a disguise, or is it becoming something else entirely? And this is the crucial difference between a physical change and a chemical change. A physical change just alters the form, but not the identity. It's still the same stuff underneath. A chemical change, though, that's a total transformation. It literally breaks and reforms chemical bonds to create brand new substances with totally new properties. Just think about melting an ice cube. Yeah, it looks different. It goes from solid to liquid, but its identity is still H2O, and you can easily freeze it right back into an ice cube. That's a classic physical change. Same if you cut up a piece of paper. You just have smaller pieces of the same paper. But what if you burn that paper? Well, you can't unburn it. You've created totally new things. Ash, carbon dioxide, water vapor. That, my friends, is a chemical change. Rusting iron, baking a cake, these are all examples where the original ingredients are completely transformed into something new. Okay, so we've got all our tools. We've got physical and chemical properties, we've got intensive and extensive, and we've got physical and chemical changes. Now let's put it all together and build the ultimate system for sorting out all the matter in the universe. So here it is, the grand flow chart of matter. At the very top, everything is either a pure substance or a mixture. Now, pure substances are pretty simple. They're either elements, like pure gold, or compounds, like pure water. The key is their recipe never, ever changes. Mixtures, on the other hand, are just different things physically jumbled together, and you can change the recipe all you want. Now, the biggest takeaway here is really understanding the difference between a compound and a mixture. A compound, like water, is brand new stuff. It's made by a chemical reaction, it has a fixed recipe, and it's totally different from the hydrogen and oxygen that went into it. But a mixture, like salt water, that's just a physical blend. The salt is still salt, the water is still water, and you can mix them in pretty much any amount you feel like. And finally, those mixtures come in two main flavors. You've got homogeneous mixtures, which are so perfectly blended that they look the same everywhere, like the air around us or salt water. And then you have heterogeneous mixtures, which are kind of chunky and uneven. You can actually see the different parts, like oil and water, or all the vegetables in that soup from our first question. All right, we have built this beautiful, logical, solid system for classifying everything. It is the absolute bedrock of chemistry. But now it's time for the twist. What happens when we zoom in? Like way, way, way in. You see, for hundreds of years, these rules were considered absolute. They worked perfectly for anything we could see, touch, or measure. They were basically the unquestioned laws of how all matter behaves. But then, as scientists started exploring the world of nanotechnology, at the scale of individual molecules, they found that these trusted rules start to bend. And then, they break completely. And here it is, the big reveal. Back in 2005, researchers looking at this tiny nanoscale world found something that just turns our whole beautiful system on its head. Down at that scale, the rules just collapse. Extensive properties, the ones that are supposed to change with size, suddenly don't. And intensive properties, the ones that are supposed to be constant, a substance's very identity, suddenly start to change with size. The fundamental difference between them just vanishes. And this is just a perfect reminder that a rule that seems absolute in our world can completely fall apart in another. It all just depends on your perspective. Which, of course, leads to one last pretty mind-bending question. If the fundamental rules of matter itself can change, what other truths that we take for granted are just sitting there, waiting for us to look at them from a new angle and be written entirely?